that we proved was the following, right? So suppose you have a matrix, the transition matrix P, for which let's say the ijth entry Pij is greater than 0 for all ij. Okay, take any finite Markov chain with the transition probability matrix whose entries are non-negative, right? And if you say alpha, therefore alpha is the minimum over all ij Pij. That means this is the minimum entry in the matrix P. Of course, this is non-zero, which is strictly greater than 0, right? Then you take for all states, for all j, you take any state, and for all n greater than or equal to 1, the following holds. Okay, so max over all I, this is Pij in n plus 1 step minus the minimum over all I Pij in n plus 1 step is less than or equal to the max over all I or max over all L Plj in n steps minus minimum over all L in Plj in n steps. So essentially times 1 minus 2 alpha. So what it's saying is if you look at the n plus 1 step evolution, that's basically the nth step difference times something that is smaller than 1. Okay, so this is strictly smaller than 1, but strictly greater than 0 as well, because alpha is greater than 0, right? Is that fine? Okay, so this is something that we proved.
Yes.
So what this leads to? This leads to the following, right? So I can iterate and basically get this, right? So it's max over all L Plj in n step minus min over all L Plj in n steps. This is definitely less than or equal to 1 minus 2 alpha over n, right? So that means if 1 minus 2 alpha is less than 1 and greater than 0, as n goes to infinity, it goes to 0. So this essentially implies the limit n going to infinity max over all L Plj of n, which is equal to limit n tending to infinity minimum over all L Plj of n, which is definitely greater than or equal to alpha, because the minimum itself is greater than alpha, which is greater than 0. That means the limit, if you look at the max of the entries in a row of the P matrix, P power n matrix, that will be in the limit same as the minimum. So that means all the rows will go to the same value. Is that fine? See what it's saying. So if you look at, for example, okay, along the columns, sorry. So if you look at P1, let's say L is 1. Okay, so sorry, not L is 1. You look at this P1, 1, P2, 1, and so on, Pn1, right? So what you're trying to do is you're looking at the max. So this is power in n steps. This is the first column of the P power n matrix, right? So you are looking at the max element and the min element. So it says both will coincide asymptotically. That means this will go to a particular vector. Let me call it as P1 as n goes to infinity. Okay, that's what it's saying. Is that fine?
Yes, sir. Yeah. So this P1 will be max or mean both, no, sir?
Yeah, both. It will be some
Okay.
number. Okay,
Okay, sir.
definitely greater than 0, right? That's what
Yeah, yeah.
it says. Okay, now let's extend this. So the second result is if you have a finite state Markov chain and it is ergodic and so on, then Pij in Pij in some step h is greater than 0, where h is at least m minus 1 squared plus 1, right? That is something that we saw. We didn't prove, but we stated, right? I stated the result. So essentially, um, so if you have m state Markov chain, right? Then if you look at the P power h matrix, right? So you look at P power h matrix. where h is greater than or equal to m minus 1 squared plus 1, then this p power h will be positive, right? So for h greater than, it is positive. Is this fine? So this is something that we saw earlier, right? Because if you look at the entries, ijth entry of p power h, it's nothing but you start from I, go to j in h steps. If h is greater than or equal to this, then this will be positive, right? Of course, you need ergodicity here. Okay. Now, what I'm going to do is for each m greater than or equal to 1, I'm going to look at
Sir,
the following. Yes.
sir, p to the power h is positive. It means that this matrix is positive definite, or sir, each entries are positive, sir.
Each entries are positive.
Oh, p to the power
It
h
is
means
positive, meaning entry wise. Okay.
okay, sir.
It's not positive semi-definite or
Hello,
definite.
sir.
Yes.
It should be positive anyway, right?
What is positive?
Each entry of P power h.
It is positive. Entries, each entry is positive. That's what I'm saying.
I mean, irrespective of h, whether it is greater than or this thing.
No, no, it's positive. Okay, I should say strictly positive,
I mean, not zero.
not zero. Yeah. Okay. Is that fine? So now we'll pick an m greater than or equal to 1. So what we're going to look at is the max over all I, Pij. I'm going to not look at h, but something larger than h. Okay, so h times m plus 1. Okay. So, and I look at the minimum overall I, Pij times h times m plus 1. Okay, is that fine? So I'm going to look at the difference. Essentially, what I'm going to look at is I'm not sure if in some steps m, this Pijm is greater than 0, but if I take h steps, I know that it's for sure greater than 0. So what I'm going to do is I'm going to look at the multiples of h. Okay, that's what I'm doing, right? So this I can apply the previous result, right? For example, we saw that, right? If I look at Pij, n plus 1 minus this is less than or equal to, in n step, 1 minus 2 alpha, right? So I'm going to apply this and bound this as follows. This is again max overall L, PLJ. I look at HM steps minus min overall I, L, PLJ, HM steps. Okay. So now I'll just multiply it by 1 minus 2 beta. So I'll define what beta is. Okay, so beta here is the
Hello,
proof
sir.
is yes.
So the above equation means if h is greater than that number, then we can go from any state to any other state with some non-zero probability.
Correct. See, essentially it says that you pick any state I, you can go to any other state J in h steps with non-zero probability where h is greater than or equal to m minus 1 squared plus 1. This is guaranteed. Okay, but you can even reach from I to j in less than h number of steps also, but this is guaranteed. If you take h steps where h is m minus 1 squared plus 1, definitely you can. Is this fine? So what I'm trying to do is I'm trying to apply this result here. Okay, so this result here, right? So this result for Pij matrix, not Pij, okay, or P matrix, P power H matrix. Is that fine? Okay. So now, what does this result in? So of course, if I look at this, right? So this particular thing now. So this is max of overall L, PLJ, H power or in HM steps. These two, I can apply a bound on this as well, right? So for example, this I can say that this is less than or equal to 1 minus 2 beta power hm, right? Or m, sorry. Is that fine? Is that fine? Because beta is defined on pij in h steps. So therefore it's 1 minus 2 beta power m, not hm. Is this fine? So what does this imply? So if I take the limit, so the limit n tending to infinity pij or max over all l plj in hm step is same as limit n tending to infinity minimum over all l plj in hm step. So this is greater than or equal to beta by definition, which is greater than 0. Okay, this is what it means. Do you agree? Okay, fine. Okay, so now I
Sir,
know
the
that
above inequality, how do we get the above inequality, sir?
huh?
Like, sir, you just replace this max over L, Pij over
Huh.
Hm minus this
Huh.
less than 1 minus 2 beta M, sir.
Huh.
How can
What is
how?
the confusion? So how do you go from here to here?
Yes, no, sir. From here to just you just said that this is a less than equal to 1 minus 2 beta to the power M, no, sir.
Huh.
So how can we do this one,
Huh.
sir?
So basically, it's this. I think we proved this result, right? This result. I don't know if you remember this. We proved this result, right? If I take Pij strictly positive, so
Yes, sir.
essentially we use the fact that the entries of the P matrix are strictly positive. I mean, it's non-zero and positive, right? And alpha
Okay.
is the minimum. And then did all this to get this. Now, instead of P matrix, what I will do is I'll take P power H matrix. You know that the entries are strictly positive,
Yes,
and I'm
sir.
going to apply this result with steps being HM and H, right? Instead of N and N plus 1, I'll take HM plus 1.
Oh, okay, sir. Okay.
Okay. So
Yes,
think
sir.
of H steps as one step. Okay, that's how you should think of this result.
Okay, sir.
Okay, is that fine?
Yes, sir. Yes, sir.
Okay, so now,
Sir,
yes.
that limit n tends to infinity or m tends to
Oh, this is, you are right. This is M tending to infinity. Okay. Yeah, you are right. This is M tending to infinity. Okay. Is it fine? Okay. So now, if you look at, for example, the this particular quantity, right? Max over all I, Pij power n, right? What can you say about this? What can you say about this quantity as a function of n? What happens if n is if I increase n? Hmm? So this should
So it will
decrease.
increase, sir.
Is it, will it increase?
If n
Increases. Hmm?
So it's a
decreases.
fraction, it will
Yes, okay.
decrease.
Decrease or increase?
Decrease.
So that's what we proved, right? So for example, we proved max over all I, Pij of n plus 1 is less than or equal to max over all I, Pij n, right? This was a trivial result that we proved. Do you remember?
Yes, sir. Yes, sir.
Because Pij n plus 1 is you go from Pi to k in one step and from k to j in n steps, summed over all k. So that is I can replace one of them by max and so on, right? That's what we did. Okay. Do you remember the proof of this? Okay, I'll probably do it quickly because this is a simple proof. You should
Yes,
know
sir.
it.
Yeah, I just break it into
Yeah, so
one step
basically
and n step.
Pij of n plus 1
Okay.
is overall k Pij Pik Pk
Into
j in n steps overall k,
yes,
right? So this is less than or equal to, right? So I can do
then
summation over all k Pik and then max over all k Pk, I'll say L Plj n, right? So
yes,
this is
get
one,
out.
so this is less than or equal to this. That's the proof, right?
Yes, sir. Yeah.
Okay, it's an easy proof. So therefore, this is non-increasing, right? It can be decreasing or it can remain constant, right? Non-increasing. And similarly, we along these lines only. So min over all I Pijn is non-decreasing. Fine. Is this fine?
Yes, sir. Yeah.
Okay. Now, because of this, I can essentially replace the earlier results. Basically, these things with the following. I'll write that and then let's see. So you look at max over all L PLJN steps. Okay. Minus. Okay. You'll have minimum overall, let's say M PMJ in n steps, right? This is less than or equal to 1 minus 2 beta power n by h. Of course, you store it. Okay. Why is this true? So why do you think this is true? So what is happening? So this is going down as 1 by 2 beta, and this is 1 minus 2 beta power m, right? So if I take hm to be or suppose I want in terms of n, right? What will happen to 1 minus 2 beta? See, hm is if I take this to be n, for example, right? Maybe n is different color. If I take this to be n, right? Then m is of the order of n by h, right? So I have to replace it by n by h. Do you agree? Right? This should be true. Okay. Basically think, why is this true? Not difficult, but yeah. Okay. So what does this mean? This implies that if you look at n also, it's true, right? So this implies limit n tending to infinity max overall L PL of in n step is same as max overall n min of overall M PMJ in n step, which is definitely greater than
Greater than 0.
0, right? Okay. Now, what is it that we have proved? We have proved the fact that if you look at the columns of the P power n matrix, as n becomes larger and larger, all the entries will be the same along the columns. So essentially, if you look at the P power n matrix as n becomes larger and larger, this whole column will be the same, right? So I mean, you'll have, for example, 0.3, 0.3, 0.3 along the columns, 0.2, 0.2 along the second column, and so on. So essentially, this will be some vector pi, and this vector will also be pi, right? And so on. All the vectors will be the same pi, right? Because each entry along the rows, right, along the rows here, they are all same. Okay, that means the entire row vector will be the same. Is this fine? Okay.
Yes, sir. Yeah.
So basically, now we'll define a vector pi as, or in fact, instead of vector, I'll just define the jth element. It's max or the limit, basically the jth entry of any row. Okay. Limit n tending to infinity max overall L. Okay. PLJ in n steps. I'll define it this way. This is same as minimum overall PLJ. Well, by the previous result, it's same as min also, right? Both max and min will be the same. So this is definitely greater than 0. Okay. Okay. So now what can you say about pi j? So if you look at Pij power n and see how far is pi j from that, right? Difference. See, pi j is limit of max as well as limit of min, right? So, and this is non-increasing and the min is non-decreasing. So basically, pi j is between the two. So this is less than or equal to 1 minus 2 beta So this implies pi j is nothing but limit n tending to infinity Pij of n. Okay. Is this fine? Is this fine, everyone? So this pi j is the limit of this pij power n. Okay. Any questions so far? Any questions? Hello? Hey, did I lose?
Yes.
Yes. Any questions?
No, sir, the line the last you have written, sir, that's Pij to the power n minus pi j is less than this.
Why is that true? See, pi j is the limit of max, and also it's the limit of, okay, let me write it fully. This is also the limit of n tending to infinity, the min over all L, PLJ of n, which is greater than 0, right? So that means in the limit, the max across the column or the min across the column, both will converge to, let's say, a number called pi j, right? So now,
Okay.
comparing this with PLJ or PIJ, how does it compare? Well, see, max over all L PLJ n, that is non-decreasing, non-increasing. That means think of it
Yes,
as
sir.
decreasing, right?
Okay. Yes,
Min
sir.
is increasing, right? That means pi j is sort of sandwiched between max and min, right?
Yes, sir. Yeah, yeah.
It's greater than max and it's sandwiched between the two. So that means Pij minus pi j also should go down like this, right? 1 minus 2 beta power n by h. Do you agree?
Yes, sir. Yeah, yeah.
Okay. So that means Pij n in n step, that are p power nth matrix, if as n goes to infinity, it goes to pi j, right?
Yes, sir.
Is this fine? Okay. 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 So now the question is, what happens to, so why, what can you say about this pi j? What can you say? Okay, let's look at what is it that you can say about. So now I'll do one thing. So pi, I'll define it as pi 1, pi 2, and so on. If there are m states, it's pi m. Okay, this is the vector. Okay, claim. Okay, let's see what is it result. What does it result in? Okay, so now suppose I have, if you take p and pi p, so what does it result in? Right, that's the question that we can ask. Do you agree? So instead,
Yes,
I'll
sir.
see what happens to pi p power n. And then also take the limit. Okay, so now if you take pi p power n, the limit as n tending to infinity, what do you think is the result? So, okay, question. Let me ask it as question. Is pi p equal to pi? Right? So, after all, we are trying to find a vector pi, which is a stationary distribution that is unique. Right? That's all we need. You agree? So, we are trying to search for such a pi. Now, we have come to a stage where we showed that this pi j is the limit of the nth power of the ijth entry of the nth power of the P matrix is pi j. So it converges to some pi j. So this pi j definitely is a probability, because if you sum over all j pi j, it's summing over all j pi j n, which is 1, right? Because these are probabilities. So this is definitely a probability, and it's strictly greater than 0. That's something that we proved. And the question is pi p equal to pi? Can you comment on that?
So it should be pi because it's a metric multiplication where p matrix every row is pi. So if we
Okay, so now, yeah, so basically you can do this, right? Simply you can see this. P power n is E pi, right? E is basically 1, 1, etc., 1, right? This is something that you can see from this, right? Okay. Is this fine? So now, if you have basically, if you look at, so okay, let's look at pi j, pi 1, pi 2, etc. pi m times p, right? That's what we need, right? This is nothing but pi 1. How do I write this? Yeah. So this. So let's look at each of these. So how do I write, for example, pi j? So let's look at how to write pi j from this. So how do you write pi j from this? So for example, if I want to write the vector pi, what does this mean? See, pi 1 is the limit of p1 jn, pi 2 is the limit of p2 jn, right? And so on. Pi m is the limit of pm jn, right? So that means basically you are looking at the columns of p, right? Especially the any columns of p power n, right? So that's what you are doing. Sorry, right? So this is essentially limit of n tending to infinity, some column, let's say the ith column of p power n matrix. Is that fine? This is what you are trying to do. You take any I, that's what you have, right? Do you agree? Or in other words, I can write it like this. Okay, maybe I'm sorry about this, so I'll be rewriting it again and again. Okay, so this is what it is, right? So if you look at p power n, right, as n goes to infinity, so what will happen? All the columns, all the rows will be pi, right? Do you agree? Is that correct? All the rows or columns? See, this is p1j. Sorry, what happens?
Rows will be pi.
Huh?
Rows will be pi of the P matrix.
Rows will be pi, right? Yeah, that's correct. So that means if you look at each row of p power n, this goes to pi. Right? Now, what happens to, so this is p, right? So now if I multiply by p, what will happen? I'll get this, right? Do you agree? Right? But what happens to this as a limit and goes to infinity? This should go to basically. Do you agree? Because as n goes to infinity, p power n is pi, right? I mean, all the rows will be pi. As n goes to infinity, p power n plus 1 is also pi, right? Do you agree?
Yes, sir, yeah.
So now this whole thing I can write it as what? Pi p. This is pi p. These two should be equal, right? Is equal to pi. Because I'm looking at each column, right? So each row. Do you agree? Stationary, right? Okay. Yeah, fine. So this is the stationary vector. Now the next question is uniqueness. Unique. Is it unique? Well, I think we saw that in the last class, right? So suppose mu is another
Yes,
vector such that this is equal to mu p, which is also equal to mu p power n. But p power n is what? Mu times, I can write it as e pi, but mu is 1, right? Therefore, it's pi, right? So that's proof that this is a stationary vector, unique stationary vector of the Markov chain. So what is it that we have proved? Essentially, we have proved that if you take an ergodic Markov chain, implies pi, which is the, or pi j, which is the limit of n tending to infinity, pij of is that correct? Yeah, is power n is the stationary distribution. is the unique stationary distribution. I'll come later. Okay, is this fine? Is this fine, everyone? Okay.
Yes, sir.
Finite ergodic Markov chain. That's what we have proved. Okay, so not for infinite or countably infinite. Is this fine? So we have proved that there's a stationary distribution. Of course, for a formal statement, refer theorem 4.3.7, page 175. Okay, of the book. Okay, so essentially, now when you have a unique stationary Markov chain. But the question is, can we relax this, right? The first question is, can we relax ergodicity? Can we relax finiteness and so on, right? The first relaxation that one can do is with regard to the ergodicity. So what you need is not really ergodic Markov chain, but you need, it turns out that you can relax this by saying if you have ergodic unichain. So what is an ergodic unichain? Remember? Did I introduce this unichain?
No, sir.
Okay. So essentially,
Sir, but we have seen, sir, in the last class that if we remove the ergodic condition, no, sir, then, sir, we can have so many such a vectors, no?
Correct. So now,
So,
sir, so what will happen? Let's look at the case, right? If it is not ergodic, suppose I have a Markov chain like this, okay? This is one class and this is another class, okay? Suppose individually, if I look at this is ergodic, let's say, individually, right? But I have one class which is transient. Now what will happen? Suppose, there is some path like this, right? Even if there is a path from ergodic to transient, then it's transient, right? It will go back to this chain. Now, if you have this kind of a chain, right, wherein you have single recurrent class, okay, so that is recurrent, right? So this is recurrent. Okay, you have some transient states. So basically, there are states in this particular space where the states are transient. Then this particular chain is called a ergodic unichain. Okay. In fact, if you have ergodic unichain, still you can find a stationary distribution that is unique. Okay. Okay, is that fine?
yes, yes.
Okay. So now, I won't go into the details of this. So you can refer to the book. So essentially, what we will mostly look into is this thing. Okay, so finite ergodic Markov chains. In fact, you can relax this to uncountable. So the proof technique will be slightly different. You cannot use the proof technique that we have mentioned, which I will. If you are interested, we can go over it sometime later. Okay, maybe after this course. Last time when I taught this course, I in fact took a slightly different approach. Proved the existence. Proved basically there are two things now, right? So if you take countably infinite, there is not. I mean, the pi itself, the stationary distribution itself, need not exist, right? Forget about uniqueness. You should talk about existence, then you should talk about uniqueness, right? I took that approach, although I didn't talk much about renewal theory and so on, although I had used tools from renewal theory without actually stating or using the jargon. Okay, so with this, this sort of concludes the Markov chain part. So I thought, as a topic of interest, I thought I'll also briefly talk about Markov decision theory. Okay, so how many of you are aware of this? This is called, let me call it as Markov decision process. Okay, maybe you would have heard of this, right? MDP. How many of you have heard of MDP? How many of you have heard of MDP? Yes.
So just heard the term. I mean, I do not know anything. Heard the term.
Okay. So what about others? Ayush?
Yes, sir.
No, sir.
Yeah, you haven't heard?
Sir,
Ayush?
sir, maybe, sir, I have read this, but I don't remember currently.
Okay, fine. So I'll briefly touch upon this now. So Markov decision theory, and it is called MDP. And let's see. I mean, depending on the time, I'll cover a few other things as well. Okay, Praveen, you were saying something.
Nothing, sir.
Okay, Jayant, you have any questions?
No, sir.
Okay.
It's like a reward system, something.
Correct.
Sir.
Yeah. It's a reward system, right? So before this, there is something known as so essentially there are certain applications which can be modeled as Markov chain. In each state, when you are in a particular state, you will get certain reward. Okay. In fact, MDP is slightly different from that in the sense that in each state you can take some action that will state and therefore the reward. Okay, that's the difference. Okay, so now let's look at the following scenario, right? So you have this is the setup. You have finite Markov chain with probability transition matrix P. Okay, let's assume this. And we will assume that if you are in state I, you will get certain reward. Okay. So suppose you are in state given, let's say xm equal to I. So what does that mean? Xm equal to I. That means in the mth time slot, you are in state I. And then a decision K is taken. That means state I and you take a decision K. Okay, so of course, that means that I should have a set of decisions. Maybe, for example, transmit or not transmit. That could be a decision. Decision K is taken. Then a reward or I K is obtained. Is that fine? So that means M can be arbitrary, the state I can be arbitrary, and if you take a decision K, Rik is your reward that you have obtained. Can somebody give me an example of such a system? Forget about, for a moment, let's not worry about Markov chain as such. So you have to model things as state and then rewards. What do you think is the right model? Can somebody come up with a problem which fits into this paradigm? Jayant?
Sir,
Go ahead.
sir, is these things are same like, sir, in a game, sir? If we reach in a certain state, then we get some reward, something like, is it modeling of that game and these are the same, sir?
Yes, to some extent. Can you be more concrete?
No, sir, sir. If we talk about the particular game, sir, so many games, sir. So in game, they just set certain levels or like certain states. Like if we get on this state, then I will get some reward, something. If I go to from this state to another state, then again I will get some reward, something like
Correct.
this.
Correct.
So
Okay,
So is
so
this
you are in the right direction. Maybe we'll refine this a little more. Praveen, can you refine or can you come up with an example like what Sumit did?
Is it like betting game or something?
You should be precise. I mean, you are in master's level, right? You can say a betting game. Yeah. What is state? What do you mean by action? You should describe. You are an engineer, right? So see, Sumit comes from math background, so he's saying something about application. So if you come from application background, so you should be able to say more, right? Ravi, can you tell me? Okay, you said betting. So what do you mean by what is the state there? What is the game or what is the problem setup?
Maybe choosing something out of some.
Hmm?
There are set of entities. I mean, if you choose some entity, you will get reward. Otherwise, you will lose the money like that.
No, I think you have to
Like
refund.
of
Okay, Rishabh.
Sir, so there was some algorithm like I heard before, like you mentioned, multi-arm bandit, where do we give some reward type of thing?
No, but you should come up with the specific application. I'm not talking about when I say problem setup, you have to relate it to an application, right?
sir? Can we model it with the like sir some insurance companies,
Mm-hmm.
like suppose sir 5-year insurance somewhere a policy
Mm-hmm.
sir in some policy if we reach to the this time then they will reward some interest or something like this.
Okay, I think again you have to refine your. So, what is state here?
Hello, sir.
So
Yes,
states are the sir time sir,
time.
like at certain time if we reach actually I can
So maybe
First
the
of all, it's
states
not.
yes
are
sir.
the
Go ahead,
so
Ayush.
maybe the so maybe the states example which Sumit mentioned, the states
Hmm.
are the number of years that we are taking the policy. So if we take the policy for 5 years, then we get some amount of interest. And
Correct.
if we do for 10 years, then some more interest will get. So like that, states will be the duration of the time we are taking the policy, and the reward will be the interest here.
I would think of that as an action, right? Whether you take a policy for 5 years, 10 years, 3 years, that's an action, and depending on the action, you get the reward, right? So where is the state? Yes, Jayant, you want to comment? You generally keep silent, and Nitish
No,
is always absent, huh? Yeah, go ahead, Jayant.
means like can we use this for packet transmission in those?
No, I think you should be precise, man. So you cannot. Hmm? Yes. Any other concrete examples that you can think of? Hmm?
Sir, is it like just say that we have an algorithm and that calculates some minimization or something, that type of problem? So we can make the algorithm work like so like in gradient descent there is learning rate we multiply. So if the states, I mean let's say one state is the minimum point, and the
Hmm?
another state is where we are starting the starting value. So when the difference is more, we are getting more step size, and that's kind of reward type of thing. Or
No, but what is the state and what is the action that you're taking?
the
See,
state
in
is
this,
like different points. Like one is minimum point and one is starting point, and between the uh, and action is like we are giving it a boost, like go slow or go.
you can think of it like that, but generally you don't do that because you can come up with the step size in a more in a non-MDP framework. Okay, so see, there are three things right out of this. So one is the state, right? The other thing is actions. The third thing is reward. These three entities, right, you have in this particular framework. Okay, so you should, whenever you come up with a problem, for example, you should describe what these three things are. Do you agree? Do you agree with this? Right? So maybe I think whatever Rishabh is looking into, right, the Wi-Fi problem, right? Even that to some extent can be framed in this particular, can be posed in this framework. But anyway, let's not be very specific. So now suppose you have this problem. Okay, so let's say there is a robot. Okay, and there is this room. Okay, and the room is divided into, let's say, smaller regions like this. I think I should not. Okay. This is your room.
The thing is that we do not know what exactly is reward to a machine or algorithm.
That you need to define, right? So what do you mean by reward? So for example, I can consider each of these regions as states. Okay, for example, these are states, right? For example, you can start from 0, 1, 2, and so on. This is some capital M. So there are M states. Do you agree? Now, for example, the robot is here. Okay, so not here, maybe in some state. Okay, so maybe this state. Here, the robot is. You start this robot, and each, so for example, in some state here, okay, there is a, let's say, excuse me, excuse me. Yeah, so there is a, let's say, a target. For example, you want the task at hand is, for example, the robot to go to the target. The target is, let's say, a water bottle or something. It has to pick it, right? So that's the target. That's the problem, right? Now the states are clear, right? The positions, basically the position is your state, right? So what will be actions? Now at least state is clear. What will be actions?
Go towards it. I mean,
no.
Move from one state to other state.
Well, the action could be simple, right? Move to the left, right, backward, front, right? Let's make it simple. Okay, so now action is also clear, right? So I take these actions, right? Then what is the reward now? What do you think is the reward? Sumit, can you tell me what is the reward? How do you mathematically define a reward here?
Sir, if I go to the target with the minimum, covering the minimum steps, then maybe I will give some reward. I can set a reward on that position. Because
No,
going to the target, you have so many ways, like, but there must exist a minimum path I can.
No, that's okay, but yeah, that is true. But what can you concretely define the reward? See, I am in state, let's say I, meaning let's say I'm in state 30th block. What is the reward? I'm in 30th block and I.
It's a distance of that block from the target.
Okay, that's good. So this distance could be your reward, right? So the closer the distance, higher the reward. Maybe inversely proportional to the distance if you want it, right? That could be your reward. Do you agree?
Yes, sir.
Okay. Now, why? Yes, go ahead, Rishabh.
So sorry, I didn't understand what exactly is reward here. I mean,
reward is the distance, right? I have to go closer and closer to the target. That's my objective, right?
Okay.
Of course, there is a bottle and you have to pick the bottle. That's another problem. But let's break it into two pieces. One, you have to go to that particular room, for example, where the bottle is, or very close to the place where the bottle is. Then you have to pick it up. Picking up the bottle is another problem. Let's not worry about that now. First, you have to go closer.
That means solving a problem is reward for that robot. Or
Yeah, so solving the problem is basically going closer to the bottle. That's the problem, right? That's what I have to do,
Okay.
right? So of course it has to pick the bottle, take the bottle and come and place it somewhere, right? The pick and place robot. But you can break that into smaller problems. First, go closer. Next problem will be pick it up. Next problem will be go closer to something, some other position, right? The fourth problem is to place that bottle there, right? These are the tasks. So I can break this into 4 pieces. So one piece is this: go from one whatever the state to a target state, right? So what are the actions? States are basically positions. Break the entire geographical areas into smaller geographical areas. Going from one place to the other is what the actions are. Basically you can go to the right, left, forward, backward, whatever, right? Depending on that. And then the distance is your reward. So now what is the missing piece here? Of course this is the problem that one can solve so that the robot can move closer and closer to the target, right? So now where is Markov here? Huh? Is it Markov?
So maybe the robot doesn't need to know where it was one step before. I mean, it only
That
depends
is
on the present
that
state
is
and
kind of true here, right? So if I'm in a state conditioned on all the past states, I just want to know what is the previous, right? What is random here? Anything random here?
random actions. I mean, it can go left, right.
Next step.
No, action.
Next.
No, right? So action also I can pre-program it, right? Go to the right, left, right, forward, backward, and all that, right? So I can do that.
Then for a finite, it's deterministic. I mean, everything target is
Everything
also
is deterministic, right? So, but still,
Sir,
this,
the path
yes.
that it will take might be the random means. Depending upon the situation, it will take the minimum path.
Yeah, for example, there is a wall here, you cannot go forward, right? So the state, those are all random, it's trying to explore. The other thing is, if you say go to the right, the assumption is you're going to right by 1 meter or whatever, right? But because of the way the robot is designed, you may not go exactly x feet to the right. You go x plus some noise. What happened? Got stuck. Oh my god. I hope is that fine? What happened? Okay, fine, good. Okay, so let's say you say that you go by x feet to the right, but what might happen is you will end up in x plus noise feet. Okay, because you cannot exactly precisely move in that direction with that speed and all that, right? There are system errors, because of which there are randomness. So I'd say that you go to the right, but you will end up in some state. You can overshot. For example, you say that these are the 3 states. Let's say you say that go by 1, you might go by 2, right? Right? There are errors. Do you agree? So that's where the randomness is. Okay, and otherwise everything else remain the same: state, action, and rewards. Okay, is that fine? And what is Markov here? Can somebody tell me what is Markov?
Hello, sir.
Yes.
Sir, if the states are fixed, I mean, then how can it move in between? I mean, how can there be some noise? I mean, in Markov, there is like fixed state, like from state 1 to state 2 precisely, not anything in between. I mean,
meaning I didn't understand.
Sir, here you mentioned like the robot has to go X step, maybe right, but it goes some X plus W. That is the randomness. So I mean, how can we the noise can be added? I mean, in Markov there was no noise or that type of thing.
No, right? So even in think of, okay, so let's look at it like this. So these are all states, okay? So now you can go from 0 to 1 or 0 to this, right? In one step. Do you agree? So I can model this as something like this, right? Do you agree? Right? Now what might happen is, if you say you go to the right, with probability p you go to 1, or with probability 1 minus p, you go to 2. Maybe you overshot. Right? Possible, right? Do you agree? Yeah.
Okay.
There could be uncertainties. Right? You can model it like this. And even the distance, the rewards, right? Even that is random. So you are saying you are in some place, but you don't know exact position, right? There is randomness in the position also. So because of which the distance, the reward that you get is also random given a state and action. So essentially what you have is the following, right? So in these things, you have a set of action space, set of states, and of course you'll get some reward, which is a positive number, right? So now according to this you have certain transitions, right? So what are those? So if you are in a state S and you take an action A, then you go to a state S dash. So there is a transition probability like this. Do you agree? And similarly, if you are in some state S, let's say, and you take an action A, you get certain reward R. This could also be random. Okay, this can be random or it can be deterministic, in which case, you know, if you are in state S and you take an action A, I can for sure say that this is the reward that you get. Okay, right? So now, for example, the way we started out here is, you know, if you are in decision, if you are in state I and take a decision K, then the reward is Ri of K. So I'm saying that, well, this is the exact reward that you get, right? Do you agree? Okay, maybe I'll just do one more thing and then stop for today. Okay, we'll continue with this tomorrow. Now we are in state I. Okay. Now, for example, so let's say you are in state I in M step. Okay. And now, suppose you go to state J. Okay. In one step, when you take an action K, right? For example, this probability I can say Pij, that is, I'm going from state I to state J because of taking an action K. Okay, don't get confused with the, I think maybe I'll just use this way. Okay. Oh my God. What happened? Okay, so that means, oh, I lost all the, okay. So now if you are in state I and you go to state J after taking an action K, the probability is I go from P to I to J because of taking an action K, let's say. Okay, this is your probability. Okay, so what will be the reward? So the reward now, this is one step reward. So what will be the reward? So if I am in state I take an action K, I get a reward of RAK. Do you agree? Right? But because of which I can go to some other state, right? I can go to a state J with certain probability, right? For example, I go to a state from I to J, right? And because of taking an action K, or I'll write it like this, right? This is the probability with which I'm going to go to state J. Suppose state J is the terminal state, I'll stop there, right? So if I go from state I to J in K steps, then I get a reward of Uj. Let's say this is the terminal reward, right? Now this can happen with certain probability, and which is Pij, but the J is any other state, right? And if you add this, this is the total two-step reward. Do you agree? Do you agree? That means if I am in state I take an action K, this is the reward, but because of taking an action K, I end up in some other state J. Being in that state J, I get certain reward, let's say Uj. So where I stop. So Uj is the reward that I get if you are in state J, and the probability of reaching J is Pij of K, and you should sum over all J, that gives you the average reward. But now I want to take an action K that maximizes this, right? So max over all K will give me the maximum reward, that is one step reward. Suppose you are in state I have to decide what is the action that I have to take, so that in the future, for me, future is just one step, right? One step ahead. in the future I'll get the best possible result. This is the problem that I have to solve. Okay, I think I'll stop with this. In the next class we will see how to iterate, keep on doing that, right? So suppose you are in jth state now, what is the reward that what is the action that I should take so that the next step will be maximized? And if you keep on doing that iteratively, you get what is known as the Bellman equation. Is this fine? I'll repeat this again, but the idea is clear, right? Jayant?
Yes, sir. Yeah.
Sir.
Is it clear?
Yes, sir.
Okay. Ayush?
Yes, sir.
Okay. I think Praveen?
Yes, sir.
Okay. Thanks. Okay, so I'll stop here. Next class, that is we need to have an extra compensation class, right? For we missed on Wednesday, so can we have it tomorrow? Is that fine?
Tomorrow by the same time, sir.
Yeah, fine. So is the same time fine?
No, sir, tomorrow I have a class, sir, from 12 to 1:30.
So tell me which time you are comfortable. 10 o'clock?
Yes, sir, no issues.
So I'll just convey either tomorrow or okay, we will have it tomorrow.
Okay, sir.
Okay, yeah. Okay.
Hello, sir.
Yes.
Sir, when will we have our end sem exam?
Okay, so let me just look at the calendar. I'll just get back because I want to get the timetable